Okay, we're going to work 10.9. It's asking us to draw Lewis structures with all important resonance structures. Maybe we'll get into formal charge for two compounds, NO2 plus 1 ion and NO2 with the fluorine bonded ring. Okay, we're going to follow our regular protocol and procedure that allows us to figure out our Lewis dot structures again. Very important skill for this chapter. Spend a lot of time on this, okay? So first step, add up number of valence electrons that we've got to work with. So how many do we have? Well, nitrogen, it's got 5 valence electrons, and each copy of oxygen has 6. All right, in its neutral state. But let's take a look at this for a second. This is an ion, is it not? So it's a positive ion or a cation. And the only way in chemistry we can make those cations, remember, we cannot add protons. The only way we can make positive ion is by loss of electrons. So I think in this case, I should actually subtract 1 electron from the total because it's a positive ion. So instead of having 17, I think here I've only got 16 for this ion because it's a positive 1, net positive 1. All right, so that was kind of one of the important realizations for this problem. Okay, when you write Lewis dot structures for ions, you have to add electrons or subtract as necessary. Now, if this was, let's say, NO3 minus nitrate, I would say, okay, how many valence electrons do I have? I've got 5 for the nitrogen. Each oxygen's got 6, right? And then I've got 1 more. So there I would add 1. And it looks like in total I'd have, what, 24 to deal with for nitrate? But here, that's a negative ion, okay? But here in this problem, I've got a positive ion. I've got to remove an electron. And so I have 1 net positive charge in my cluster, okay? That yields 16, right? So practice that a little bit for writing Lewis dots for ions. Your book sometimes doesn't do a great job of considering ions. So you're going to have to do that on your own because it's important, right? All right, nonetheless, we've got 16 to use. What are we going to do? Got to figure out what our central atom is. Nitrogen has a lower group number than oxygen. As a consequence, it's going to be our central atom. And it looks like I've got 2 atoms of oxygen that I need to connect with bonding pairs. I do that with single bonds at first because I've got to hold the whole cluster together, and then I kind of see where I'm at. I do that by completing my octets. So I'd have to do 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. It looks like the central nitrogen needs 4 more. So I've got 6 lone pair electrons, 2 in the bonding pair, so this oxygen's got 8, as does this oxygen, so those 2 oxygens are happy. Central nitrogen as written, 2, 4, 6, 8, it's happy. Now how many electrons have I used? 6, 12, 14, 16, 18, 20. I've used 20 in that structure that I proposed. That is not going to work, is it? I only had 16 valence electrons to use. The structure requires 20. Not so good, all right? So I need to change this. That means that this is not correct. I need to change it. Now, if I have fewer electrons than what I've used in my structure, that basically means that I need to share more. So, for instance, maybe I take a couple lone pairs and I make some extra bonds. And here, since I'm 4 deficient, that basically tells me that I need 2 more bonds. Okay, if you take the number you are deficient and divide it by 2, that tells you how many more bonds that you need. Okay, so I knew that I needed 2 more bonds, so I added 1 bond here and 1 bond over there. Okay, you see that? And as a result, I think this is going to work. So I got 4 non-bonding electrons. It looks like I've got 2, 4 bonding right here. I don't have any lone pair electrons on my central nitrogen right now, do I? But that's okay because it's participating in sharing 8 total. I've got another 4 bonding electrons here, and another 4 lone pair on this oxygen. So it looks like now, with this new structure I proposed, I've used 16, and that's what I had. So, great news. I got it, right? I got my Lewis dot structure for the NO2 plus 1. Now, actually, I hadn't completely finished this, because what I should do to polish this up a little bit is put that in a bracket and a plus sign right there, okay? That's important because I want to tell the world that that's a +1 cation, okay, and not a neutral molecule. Now, how could we figure out that maybe that was the case, even if I forgot to put my brackets in the plus, okay? We could assign formal charges. Formal charges, right? Let's see. Formal charges is, again, if you're going to compute that, it's a computation for each atom. It's the number of valence electrons assigned from the periodic table, basically. Okay, kind of like these numbers that we started with. Basically, a minus the number of electrons given in structure. Okay, so let's assign a formal charge for the central nitrogen right here. So from the periodic table, you see that you're assigned 5 for nitrogen. Now I'm going to subtract how many are actually assigned to it. Now what's assigned to this? Well, I just got 1, 2, 3, 4 bonds. These are all bonding pairs. Each line represents a bonding pair for a total of 8 electrons. Now, are those 8 given to this nitrogen alone? Well, no, because they're shared with oxygen, right? So each of these lines are shared between the oxygen and nitrogen. Now remember, when you're computing formal charges, you assume that the electrons are assigned or shared equally between the bonding atoms. And as a result, I would say that half of my 8, or 4, could be assigned to this nitrogen. So 5 minus 4, and it looks like that equals a +1. That's my formal charge, then, on that central nitrogen. The formal charge is indeed a +1. Now, if you go about doing the same calculation, so nitrogen's +1 formal charge. If you go about doing the same exact calculation or computation for the other atoms in this compound, for the oxygens basically, you'd find that they have a formal charge of 0 and 0. Because it's 6 from the periodic table, and there's 1, 2, 3, 4, and then half of these, which are 4, so that's 6. The sum of the formal charges, 0 plus 1 plus 0, has to equal the charge on the ion. So here we see how that can work out, okay? All right, so that's the first half of this problem. Now the second half is a different compound, it's NO2F. But you go through the same exact protocol and process. Nitrogen's got 5 valence electrons from the periodic table. Each copy of oxygen's got 6, and my fluorine's got 7. So if I add all those up, I think I've got, what, 24 electrons to build my molecule with. Now I'm going to look at these elements and figure out what to put in the center. And this one's a little bit hard because all of these are pretty electronegative. But the element with the lowest group number is nitrogen, which usually goes in the center. And then the other atoms are connected to that. Now it looks like I'm going to have at minimum 3 more bonds to make this work. Okay, because I got to hold the molecule together. I've got to hold that nitrogen to oxygens and some fluorine. So I'm going to come up with this sort of first draft of what my Lewis dot structure might look like. And I'm going to roll from there. Now what do I do next? I have to complete my octets. If I'm doing that for this particular rough draft, I do 1, 2, 3, 4, 5, 6. Make these dots a little bit bigger so they're easier to see. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And again, what I'm doing here, and it's 20, okay, not to lose track, 20 lone pair electrons. What I'm doing here is I'm adding the dots or the lone pairs of electrons wherever they're needed, to complete the octets, right? So 1, 2, nitrogen's involved in sharing 6, that makes 8, right? The oxygen, 1, 2, 3, 4, 5, 6, it's involved in sharing 2. These 6 plus these 2 sharing make 8. So they complete the octet. That's the driving principle here behind these Lewis dot structures, okay? So right now I've got 20 lone pair electrons, and it looks like 6 bonding pairs. That makes 26 electrons. And how many did I have? Oh, I only had 24 to use, right? So that's not going to be something I'm very happy about, because I've only got 24 to use, and the structure that I've proposed suggests that I've got 26. So I need to modify my structure. It's incorrect as it's currently written. And this is an important skill for you to recognize when the structure is incorrect and you have to modify. Now, based on this little rule of thumb that I talked about in the previous example, how many additional bonds do we need? Well, I used 26, I only had 24, that's a difference of 2. If you take the difference or deficiency and divide by 2, that tells you how many extra bonds. So here I'm going to need 1 extra bond. If I add 1 extra bond somewhere and get rid of some lone pairs, this is going to work. And that's going to be my strategy. The question is where do I need to add that extra bond then, okay? Oh, I should probably keep that with me. Now, one candidate is adding an extra bond to fluorine. But that doesn't make sense because fluorine usually likes to form only 1 bond. And it's done reacting, so I can't really add there. But oxygen usually likes to form 2 bonds, okay? So one thing I could do is add a second bond here, pi bond. And then if I did that, then I would have 1, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now this structure uses 24 electrons. And that's what I had. So that would be a valid Lewis dot structure for this compound. You think that we can come up with a different structure as well that might also be valid? How about if we shift around where that double bond is? Not making it to fluorine, because fluorine usually likes to form, like I said, only 1 bond, but maybe I could write a resonance structure, a resonance form, where I put the double bond over on this side to this other oxygen. Okay. Oh, it's got this symbol now. Okay. So I basically flip-flop where the double bond is. I put it on the right instead of the left. And again, these 2 structures are called resonance forms of one another. Okay, resonance forms. Now, why in the world is that important? Again, it's important because if you were to go into a lab and try to make measurements that differentiate between this bond and this bond, you'd have a really, really difficult time doing that, okay? You can do complicated experiments where you try to put a certain isotope of oxygen here and a different isotope over here and try your best to figure out which one's the double bond and which one's the single bond through complicated laboratory experiments. But those experiments generally fail. And the reason why is because in such cases, you cannot tell the difference between these 2 bonds, between the nitrogen and the oxygen. In reality, both bonds are experimentally equivalent, or the same, basically. Okay. Now you say, well, you got to have a double bond somewhere. It's got to be here or here, but it's really both places simultaneously, I guess you could say. And that's the idea behind resonance in Lewis dot structures, is that these bonds would experimentally appear to be exactly the same, even though the Lewis dot structure says one of them's got to be a double bond, one of them's got to be a single bond. In reality, they exist as a hybrid. Okay, somewhere in between a double and a single bond, each one being experimentally equivalent. And again, that's an important idea here as we're attacking these Lewis dot structures. If I want to calculate formal charges, what would I come up with here, okay? So this oxygen, I think, would have a formal charge of 0. And the reason being is 6 electrons from the periodic table, 2, 4, and then half of this, which would be 6, okay? What about this fluorine? I think that one had a formal charge of 0 as well, if I'm not mistaken. It's usually fluorine likes to form one bond, and it gives it a formal charge of 0. But just to demonstrate that, how many electrons in the periodic table? 7, right? 7 valence electrons. And 1, 2, 3, 4, 5, 6, 7 when you share, right? So that would be a formal charge of 0, 7 minus 7. And I think these two might have opposite formal charges. So let's take a look at the central nitrogen here for a second. This nitrogen right here, what's its formal charge? Well, it's got 5 on the periodic table, 5 valence electrons. How many are assigned to it? Well, it's got 1, 2, 3, 4 bonds. And if we predict sharing equally, I think it's going to have a +1 formal charge here. And what about this oxygen over on the far left? Okay. I want to compute its formal charge. What's the value from the periodic table? 6, right? Valence electrons. And how many are assigned to it? Oh, it looks like there's 7 assigned to it right now. So it's got a -1 formal charge right there. These two cancel each other out. You get a net 0, and that's good because this molecule is not charged, and that's what we've got to get, okay? But again, having formal charges in structures is generally not a good thing for the structure's stability. And if you must have formal charges, it's usually better to have negative formal charges on atoms which are more electronegative. That tends to be a little bit better. So having this +1 on a pretty electronegative atom is not so great. But I think here we're kind of forced with it. We don't have any other choice. All right. So again, practice this Lewis dot structure business. It's important.